go. Okay, so we continue on. So last time we finished up, what was it? I know that oh yeah, we did surface area of revolutions. So we're done with that. Now we're gonna start using a lot of this stuff that we learned and apply it all over the place. Okay, that's not what I wanted to happen. There we go. Oh yeah, let me spotlight myself. Someone's like stealing my spotlight. Okay, so let's just sort of like talk about what we're going to be doing here. So we have learned this technique. Okay, why is my thing not working? There we go. So we've learned this technique. We've learned that if you take the limit as n goes to infinity of a sum f of x times delta x, that we can solve that with a definite integral. And the fundamental theorem of calculus makes it even easier. It says, well, find the antiderivative and plug in b and plug in a and subtract them. Right, so this part here is easy, quote unquote. Okay, I want that to look pretty. This part here, this is the easy part. Does everyone get what I mean by it's easy? Like, it's not too hard to find the antiderivative usually and plug in two numbers and subtract them. The hard part of actually using this to do something useful is this damn part here. Right? Like, actually setting this up. And we've used this trick in several different contexts, right? Like, we first started with this idea that that f of x times delta x was equal to the area of rectangles, right? And we use that to approximate the area of under some curved function, right? Does everyone remember that? Like, that's the first. We came up with the idea of the Riemann sum. We took the limit of the Riemann sum, and we're like, oh damn! Like, I was able to calculate this area by taking the limit of the Riemann sum. And then we got like more complicated with all of this. So like, we used the same idea to calculate things like arc length, right? So remember, instead of f of x times delta x was the area of rectangles, in that case, f of x times delta x was what? If you're talking about arc length. So like, what is it that we approximated when we were trying to calculate arc length? Yeah, the length of a line segment. Notice, we ended up just taking the limit of your sigma, your sum, but like the meaning of what you were adding together was different. So like, at first we were adding together areas of rectangles. And then we're like, oh shit, why don't we just do that with the lengths of line segments? And then like, when we were doing surface area, it was like, shit, why don't we just let f of x times delta x be equal to, what was it? It was like the surface area of frustrums. Right? And we added those together, and then when we took the limit, that gave us our surface area. Oh, whatever. Okay, we're gonna let him chill out for a second. Okay, what else have we done where we were like, oh, what else have we used this method for? We've calculated arc length, surface area, there's like at least one more. Yeah, volume. That's good though. We've used this to figure out volumes, right? With the shell method, the disk method, the washer method. What changed always is what your f of x times delta x was. For these, like for the shell method, I want to say, ooh, what the hell? For the shell method, we were taking the volume of cylindrical shells. For the disk method, it was the volume of disks, right? Like, the whole idea is that it's the same idea, but the interpretation is changing each time, right? And I usually spend like a good half an hour to an hour like explaining how I set up this approximation. And then how does it always end? Well, we take the limit of the approximation and solve it with a definite integral. Okay, you do this a lot in like physics, chemistry, computer science. So it's like an idea that you need to be able to understand, because they're just going to be able to assume that you're going to be able to do this. Does that spiel sort of make sense? Like there's like a bigger thing that you're supposed to be noticing that we're repeating like over and over here. Hopefully you see that. So let's do this with some physical applications. Okay, so first of all, we need to talk about some terms here. Okay, what is mass? We have like some terms. So when we talk about mass, I guess you could call that like, oh man, it's sort of like a fundamental thing. It's the amount of stuff, like physical stuff, right? Not like volume or anything like that. So mass is different from volume. Volume is a measure of extension, or a measure of space. Oh, the amount of matter? Yeah. So we use the less precise word stuff. Like, it has to be tangible. Now, volume, on the other hand, is a measure of space. And if you put these two together, what's a new unit that you can come up with? Yeah, density. So density is usually defined by the Greek letter rho. Sort of looks like a weird P. And density is the mass unit per volume unit. Wait, yeah, it's mass over volume, right? Not volume over mass. Let me look that up. Yeah. So it's mass per, there's several different ways you can do this. Mass per some sort of measure of space. Okay, so we're going to talk about that. So we're going to start with a... There's actually a bunch of jokes about this. And I'm going to show it to you. Oh man. Physics jokes are funny. Oh man, I can't find it. I was actually on Instagram the other day looking at some of these memes. They're like hilarious. Oh damn, I can't find it. So anyways, I guess I'll just sort of tell you how the joke works. Usually in physics, like, they make a lot of weird simplifying assumptions. So this is an aside. Physics is famous for simplifying assumptions. Some of the greatest hits include things like, assume that the penguin is a cylinder. Or things like, usually this like pisses people off, assume there is no friction. A lot of the times when you're like learning physics, like they'll just say something where you're like, that doesn't seem like very practicable. And they have to do this because otherwise you wouldn't be able to solve the problem. There's like a greatest hits of like meme things about this. I highly recommend you go on like Instagram and like different things and like look for them. There's a lot of very funny physics memes pages. But anyways, So we're going to make some assumptions here is like basically what I want to say. So we're going to talk about something called linear density first. So what's linear density? Linear density is where density is mass per unit length. All right, we're going to think of things as if like they were solely two-dimensional, which I don't think you'd be able to have mass in that case, but whatever. So that's like what made me think of this. Like if you have a two-dimensional object, it probably has no mass, right? So it's sort of weird to think of the idea of like linear density. So whatever. Hopefully you get the joke. Maybe not. So let's like draw a picture here. You've got your... Yeah, if you rotate it around the x-axis, boom, you've got density. And that's exactly what we're going to end up doing. But, like, it's a little weird to say, like, at first, like, oh, there's this thing. It has no volume, but it has density. And I was actually thinking about that as that's what why I thought of the physics meme pages. So let's say here's your x-axis. And let's say you've got, like, a little rod. Draw in a rod. Okay, that one's not good. I don't like it. Let's copy this one. Oh my god, burrito. Jesus. Okay, here's our rod. Yay. So does that make sense? Like this is like a little rod here. Okay, because it's a rod, you can sort of think of, you can basically, let's assume that the density, so here's our assumption. The density only varies with the x-axis, which probably never happens in real life, but let's just assume. So the idea would be that, like, if you look at some cross-section of it, like right here, what can you say about the cross-section? Or what can you say about the density at all the points in that cross-section? It's constant. Does that make sense? Like, that whole little segment right there has the same density, which will be different than the density somewhere else in the rod. Okay? So, why is it not letting me type? There we go. If the density was constant, what would a formula for the mass be? Well, you would take whatever your density is, which is rho, and then multiply by how long the rod is. So assuming that the rod starts at x equals a and ends at x equals b, does it make sense that the length of the rod is b minus a? Right, so it's some length b minus a. How would you find the mass? Well, by multiplying the length by the density. But that's assuming that the density is constant. What if the density is variable? What then? Okay, that's why we need this function which will give you the linear density. So we're going to have a density function. So rho of x is equal to the density of the rod at some x value. So you can imagine, like, I don't know, like maybe maybe the rod begins as a really not dense on this end, but as you head to the right, like maybe it ends up being very dense. I'm like not sure how you would actually make such a thing, but does it make sense that you could have a rod where it's like on one end it's not very dense, like somehow they're able to make the metal so that like it's like lighter, and then as you move along the rod, like there's more and more metal used in the same area, so it becomes more dense somehow. I'm not sure how we would achieve this, but does that idea make sense? Like the density of this thing is changing depending upon where you're looking at it. Are we good with that idea? Okay, cool. Okay. So, how do we always solve these problems? We estimate / approximate, and then do mathematical magic to get the... That's basically what integration is. You're like, fuck it, let's just estimate it. I'll take a limit, and then like something will happen and I'll get the right answer. I guess I should replace do mathematical magic with take a limit. Right? Taking the limit is like the magic. You're like, let's just estimate it, we'll take the limit, and then boom, like you get your answer. Okay, so we're gonna do that here. So we've got our rod. Let's draw in our rod. My beautiful rod. Okay, so you could split the rod into n segments, right? That's how you always start your estimate. Right, remember when we were trying to find area or volume? What do we always end up doing? We're like, oh, let's just imagine you break it up into 4 pieces. Let's do that. So we'll draw the picture with n equals 4, but like it's arbitrary, right? So here was x equals a, here was x equals b, and we're like, I don't know, let's just split it up into 4 pieces. Right, so you have your x naught, which will be the point right here, and then x1, x2, x3, and the 4th point will give you right there, right? Okay, so you've got like the part of the rod right here. You've got the part of the rod right here. You see I'm changing the color so we can like tell the different parts of the rod. You've got like the part of the rod right here. And then you've got the part of the rod right here. It looks like the Italian flag or something. It's my Italian flag rod. Okay, so let's look at one of those pieces, which goes, say, between x3 and x4. Okay, there's like my rod section. Okay, so how wide? So what is the formula for the average density of this segment? So what's our formula to find the... Actually, I'm sorry. Erase. I don't want to say that. We want the mass, right? Yeah, we want a formula for mass. So we want to approximate the amount of mass. So the mass of this fourth component is approximately equal to some amount of density times the length of it, right? And the length is going to be equal to delta x, right? Because x3 minus, well, actually, let's just write this. The length is x4 minus x3, but what do we know that x4 minus x3 is going to be equal to? Delta x, right? Like, remember that's like our whole point about why the points are always equally spaced. So you can always just have like x4 minus x3 is delta x, x3 minus x2 is just delta x, and so on. Okay, so you need to know, like, well, how am I going to figure out my density? Because my density is not constant along this, right? So what would be a nice point to choose? Like, where should I, between x3 and x4, where should I choose my the x value to plug into my density function? What would be a good choice between x3 and x4? Especially if it's like linearly changing. Yeah, halfway. You probably just want to choose the midpoint. So I'm going to call x star the midpoint. So we probably just want to do the density in the middle times the length. Yeah, so I would choose x of x 3.5, but we'll just call it x star. So you're like, I don't know, just choose the point in the middle, plug that into your density function, multiply that by how long it is, and then that will give you a pretty decent idea of what the mass is. So, if we wanted the total mass of the rod, what are you going to do? Well, you're just going to say, let's just take the sum from I equals 1 to 4 of this formula. All right, just x star will be the midpoints for all those different sections. Boom. Now looking at this, you're like, oh damn, what do I got here? This is just a Riemann sum. Right? This is your f of x, and this is your delta x. But now, what's the interpretation of f of x and delta x? It is no longer the area of a rectangle, it is now the mass of a rod segment. Do you see how this goes back to this, what, f of x and delta x, the product of those two things, like the interpretation of it is just changing depending upon what it is that you're trying to calculate. In this case, we're adding up a bunch of masses, right? Before it was other stuff. So how will we end up getting the actual mass? This is just an approximation. So what will the actual mass be? Like, what do we always end up doing? Yeah, we take the limit. We're like, okay, cool. The total mass is actually equal to the limit as n goes to infinity. So in other words, we increase the number of little segments that we break the rod into. And we add together the masses for each of those little segments. How do you find the masses of each of those little segments? You multiply the density times the length of the segment. And then you realize that all that is integrating from A to B your density function. Boom. So you're like, oh wow, okay, so apparently if my density only depends upon the x value, I can just integrate that from A to B and then bam, I get how much mass is in there. Okay, so we're going to use this to do an example. Okay, so let's say that you have a rod. Example. somehow you make a rod whose density is linear, i.e. the density only depends on the x value. If the density function is equal to the sine of x, and the rod is on the interval 0, 1. So in other words, the rod starts at x equals 0 and ends at x equals 1. Actually, no, let's go from pi over 2 to pi. What is the total mass of the rod? Okay, so this is like a really weird rod because let's draw like a little x-axis. This will be 0, pi over 2, pi, 3 pi over 2, 2 pi. So the density depends upon sine. And the value of sine looks like this. Between 0 and 2 pi, right? Okay, now, where is our rod defined to be? It goes between pi over 2 and pi. So we're looking at this region right here in green, right? So at the beginning of the rod, what is the density? Like, at that little thing right there, it's how many units of mass per unit of volume? One. Okay, cool. Now, at the end of the rod, this is a little weird. What is the density? 0. So this is like some weird rod. It starts off right here at pi over 2, and it exists. It has a density of 1. But what happens to the rod as you move over to pi? Like, effectually, like, what's happening? Like, what happens here at the end at pi? Yeah, like, you could sort of, like, imagine, like, you know how, like, they have that cool CGI effect where something, like, fades out to transparent because it doesn't exist anymore? Yeah, it's sort of like that. Like, it starts off, like, having a density of 1 right here. A density of 1. And then over here, it, like, literally fades out of existence. Like, at the very end, like, it has 0 density. So, like, if you color code it, like, if red means very dense, it starts off very dense over here. And then, like, blue will mean that it's not that dense anymore. And then at the very end, like, there's nothing left, right? It just sort of, like, fades out to ghost. I don't know how the hell you would achieve this, but let's just say somehow you did. Okay, cool. So, basically, all we need to do to solve this, we found out, is, well, integrate from pi over 2 to pi of our density function. Our density function is the sine of x dx. And what's the antiderivative of sine? It's a minus cosine. So you could factor out a minus, and you get minus cosine of pi minus cosine of pi over 2. And what's the cosine of pi equal to? So if you draw the cosine function, the cosine of pi is -1, right? Yeah. And then you subtract cosine of pi over 2. What's the cosine of pi over 2? 0. And so the 0 obviously goes away, and negative of -1 is +1. So how much mass are you going to need to create whatever the hell this rod is? 1 unit of whatever mass you're dealing with. So let's say you have some like manufacturing process that makes this rod. Boom. That's how much stuff you need to input into it. It doesn't matter in this question, but would it be cosine pi plus because of the factored -1? No, because I'm factoring out the -1 from the antiderivative itself. So normally you would have had a minus on both of these, right? But you still it's still f of b minus f of a. And then I factored out a negative from both of them, and that's why that's why this minus stays here. That's a good question though, because like that's a very common mistake to think like, oh, shouldn't it be plus? Because I'm not getting the negative from the minus between them. It's from the minus is in both of the antiderivative. Right, yeah, exactly. So then when you factor out the minus, you get cosine pi minus cosine pi over 2. Okay. Okay, so we used our idea. Oops. We came up with our idea. Notice the hard part was figuring out that this was justified, right? Once we knew that we could do this, it was rather easy to simplify it, right? And that's something I talked about at the beginning, right? You remember up here, I basically was like, right? The easy part is once you set up the integral and just use the fundamental theorem of calculus. The hard part is like knowing where the numbers go and like what the meaning of it all is. Okay, cool. Making sense so far? Okay, so we calculated mass with a linear density. Now we're gonna talk about the mass with radial density. This actually is used a lot. So now we're actually gonna operate in like 2-dimensional space explicitly. Okay, so what's the idea here? We have a circle. Let's draw in our circle. Okay, cool. Say like the origin's like right here. So there's our center. Okay, and now, so we have this disk. And let's just assume, so the assumption here is that the disk is thin enough so that, oops, let me scroll down a little. The disk is thin enough so that we can think of it as a 2D object. Right, does that make sense? Like you have some sort of like hockey puck, but there's so little depth to it that you basically, as far as you care, it's just a disc. Okay. Sort of like how the rod was like pretty close to being a 2-dimensional object. It looks like a line. It's like a fat line. Same idea here. Okay. So, and we're also going to assume, actually we have several assumptions here. Assumption. Let's put assumptions. The disk is thin enough so that we can think of it as a 2D object. Next assumption. The density is in terms of unit area. So previously, the density only depended upon the x value. Well, actually, this is the cool thing. Really, calculus is just a class where you learn all the relevant math for physics and a bunch of other stuff. And actually, this is a good way to think of it, because does anyone know when most of standard physics was invented, as well as calculus? Yeah, Newton. And, well, actually, there's one other dude, too. Newton gets most of the credit, but there's two dudes who figured this all out. Yeah, German guy, Leibniz. Leibniz, I think, was the better mathematician, but we live in the Anglophone world, so people mostly give the credit to Newton. But interesting thing, they basically invented calculus so that they could solve physics questions. So, like, Newton was famous, for, in classical mechanics, there's, gravity and that sort of shit. Leibniz did a lot of work with, kinetic energy. I was a physics major. Not a physics major, a philosophy major. And I remember actually reading some of the papers that he wrote, trying to justify, does anyone remember the formula for kinetic energy? What's the formula for kinetic energy? Yeah, 1/2 of mass times velocity squared. What is this really similar to? There's another formula which uses very similar terms. So kinetic energy is 1/2 of mass times velocity squared. What's another very similar term in physics? Close. It just has the variables. Very similar to kinetic energy, but not quite. All those formulas are very close, but not the one I want. Something similar. I'll give it to you. What's this formula? Or there might be a 1/2. What's mass times volume called? What's mass times volume? I'm sorry, mass times velocity, my bad. I meant mass times velocity, not mass, momentum. Interesting thing, there was, at some point, people were like, you only need this one. And another group was like, you only need this one. We're momentumists here. And then other people were like, fuck that shit, kinetic energy is the shit, that's what we care about. There's actually reasons why you want to work with both, but what's the primary difference between kinetic energy and momentum? Conceptually, there's something really important about one of them that the other one doesn't do. They both involve mass and volume. Does anyone happen to know? Conceptually, something happens with one of them that doesn't happen with the other. So something happens with momentum that does not happen with kinetic energy. What is it? I'm going to start writing it. Let's see if anyone can get it. It is close to constant. It is conserved. Has anyone ever heard of the conservation of momentum? Okay. And there's some interesting, very deep mathematical ideas that explain why that's the case. Calculus is invented to calculate these sorts of things. There are other more advanced calculus topics that would tell you why in certain situations you'd want to deal with momentum versus kinetic energy or something. Because kinetic energy is not conserved, but momentum is, and there's some interesting reasons why. So at some point, people were battling this out. They were saying look, this is the thing you want to look at. Yeah, energy from motion and mass in motion. Yeah, so it's like one of those is conserved and like one of them isn't, and there's like some cool reasons why. And like yeah, physics is sort of crazy because like there's all this math that explains basically the like why you'd have these ideas about physics. So just I wanted to point that out. Anyway, so back to the radial density. We have that this disk is super thin. You can basically think of it as a 2D object. The density is in terms of unit area, and the density only varies along the disk's radius. So the density is in terms of unit area, and also the density only depends on the radial distance. So in other words, let's say that you move out some distance from the radius. Well, every other point, which is also that distance from the radius, is going to have the same density, right? So all the points on that red circle, they have the same density. All these points have the same density. And there's actually some practical reasons about why you'd be interested in this. Has anyone ever seen like glass blowing? Or how they like make walks? A lot of objects, when they forge them, they spin the object. And if you spin the object, that means that your mass or your density will depend upon your distance from the point at which you are spinning it, right? So does it make sense if you take a bunch of metal and you heat it up and then you spin it, they'll form some sort of shape? And then how much the density of the metal will depend upon the distance from the radius about which you are spinning it. So like there's like real reasons about why you'd want to make these calculations given the manufacturing techniques that you have. So like I was actually thinking about that the other day and I was like, oh, it actually makes sense why they'd want to do this. Like now not so much with 3D printers and stuff, but whatever. At some point maybe people will have to like build shit that way again. So anyways, so we want to calculate the mass. Now, the mass, sorry, the density is in terms of unit area, right? So the mass is going to be equal to the density function times the area of the thing that you're dealing with. So remember how before your mass was equal to the density times the length? Now it's density times an area. Okay, so we're going to need to split this shape up into different parts. So we're gonna let's split it up into let's split it up a little more. So let me show you how we're gonna do this. So remember how before you had a line and we split it up by breaking it up into parts? Now, because we're doing things radially, we're gonna split up our disk into like different segments by drawing different circles. So like if you draw a radius right here, yeah, concentric rings, exactly. So like the center would be like your x0, this point right here would be like your x1, I'll zoom in so you can see it a little better. Okay, so you've got your x0, you've got your x1, this point right here would be like your x2, and that point right there would be like your x3. Now, I didn't draw it very well, but does it make sense that they should be equally spaced? Actually, let's just redraw it. redraw this thing because I did like a shit job. Okay, so let's draw some circles. Okay, there's one circle. Here's another circle. Here's another circle. And finally, one more. There, this one's actually not that bad. Boom! So if you, if you draw a radius out, the center would be your x0. This point right here, we'll draw it in red, that intersects the next concentric circle would be x1. The point which intersects the next concentric circle would be x2. The point which intersects the next concentric circle would be x3. And then finally you'd have one more, you'd intersect the next concentric circle, that would be like x4. Oh. Okay, now let's choose one of these. Let's choose this one. This like little ring here between x2 and x3. Now, what do you know about the distance between each of these points? Like between x3 and x4, x2 and x3. What do you know about that change in the radius? It's always delta x, right? Yeah. Okay. And what do you know about the density in the section between x2 and x3? Like, how does the density change? Well, actually it does. It doesn't change according to the radial distance. So if those 2 points were close enough together, if delta x approaches 0, you'd get a circle, and then the density would be unchanged. But what we can do is we can take the midpoint between x2 and x3, and that's probably on average what the density is. All right, so remember how before I took that midpoint? I'm going to take the midpoint right here. So I'm going to take my density at the midpoint of that little concentric circle, or the 2 concentric circles. Now, what do I need to multiply the density by? The density of that ring, right? And how do you find the area of that ring? Well, you're going to have the area of the bigger circle minus the area of the smaller circle. So the area with the radius of x3 and the area of the radius of x2, right? So you need to subtract them. So the area of the big one is pi x3 squared, and the area of the other one is pi x2 squared. You can factor out a pi, and x3 squared minus x2 squared can factor into x3 minus x2 times x3 plus x2. Right? And there's a change you can make. One of these is equal to something. What is one of these equal to? scroll up a little, maybe you'll see. So what do we know about the distance between x0 and x1, x1 and x2, x3 and x4? They're all equal to delta x, so which one of these is equal to delta x? Yeah, x3 minus x2. This is delta x. Cool, so we'll make that replacement. Now, this one over here, x3 plus x2, it's equal to something else. So I'm gonna like draw the picture so you can see it. Like, here's my circle with radius x2. And here's my circle with radius x3. So as delta x goes to 0, actually, and what's between them? What's between x2 and x3 that we talked about earlier? Well, x star, which is their midpoint. I'm sorry, I have like a really bad drawing there, but yeah, this is the x star. Now, as delta x goes to 0, what happens to x2 and x3? They get closer and closer to each other, so what would they actually converge to? So as delta x goes to 0, x3 gets closer and closer to x2, and what do they both approach? Well, not 0. They don't approach 0. The distance between them becomes 0. There's like a sandwiching effect going on. If x2 gets closer and closer to x3, what are they sandwiching? And thus, what are they both approaching? X star, exactly. So if you were to take the limit of this, what would x3 plus x2 end up being equal to? Yeah, exactly. x3 plus x2 becomes 2x star. Because x3 and x2 both approach x star, which means you get 2x star. And now we can rewrite what all this is. It becomes equal to, if you take the limit, 2 pi x star times delta x, which if you think about it, what's the 2 pi x star? Like, geographically. The circumference of, the circumference of the circle in the middle of that little ring. Yeah. And then delta x is the width of the thickness of the ring. These are called annuluses or annuli, right? Those like little area that I like highlighted over here. This like disc thingy. Cool. So now we can find a formula here. So our mass is approximately equal to our rho x times the area. The area of one of those things is 2 pi x star times delta x. So if we wanted to find the total mass, you're going to add together each of those individual masses, which will be your 2 pi x star times rho x times delta x. Right? We just got that from all that crazy calculation we just did. And that's an approximation of the total mass. What will I do to it to get the actual total mass? Yeah, take the limit. So in other words, instead of adding up like n of those little ring thingies, you're gonna add together infinitely many of those little ring thingies. So you take the limit of sigma I equals 1 to n of 2 pi x star times rho x times delta x, which now is a definite integral. We'll talk about the limits in a second, but you're going to take the definite integral of 2 pi x rho x dx. So if your thing only has radial density, you can find the mass by integrating this. Oh, damn. Wow. I actually went like the whole time here. Oh, actually we went over. My bad. Sorry. So I'll just tell you, you integrate from 0 to r, being because you start here where the radius is 0 and you work your way out. Or sorry, you start here where your radius is 0 in that circle, and right, you work your way out to the biggest radius, which we call r. So we'll continue this next time. So there's your formula, though, to find the mass if you only have radial density. Okay. Wow, that was a lot, was it not? Did I crush you? I'm sorry if I did.